All right, in this video, I want to talk you through Chapter 9, Predicate Logic, the first couple of sections, sections A and B. So to begin with, let's learn how to translate ordinary language sentences and propositions into predicate logic. And then secondly, let's learn 4 new rules of inference. Now, in this chapter, you're going to need to retain all of your implication rules and your replacement rules that you learned in Chapter 8. We're just going to be adding several more rules to that toolkit so that you can solve proofs and proof problems in predicate logic. So predicate logic was pioneered in the early 20th century, primarily by Gottlob Frege, the great German logician and philosopher. And the cool thing about predicate logic is that it combines the benefits of both categorical logic, that is the logic that deals with statements beginning with all, some, or no, and propositional logic, such as we've learned in preceding chapters. So without going into that, that's really a revolutionary breakthrough in the history of logic. All right, the fundamental units in predicate logic are predicates. Now, predicates, if you've been to English class and you think back on grammar, they involve verbs, and they are distinguished from subjects. So, for example, let's take a sentence like this. Abraham Lincoln was a lawyer. The grammatical subject of that sentence is Abraham Lincoln. The predicate is what we're saying Abe Lincoln was or did. So the predicate is was a lawyer. So in predicate logic, we're going to symbolize individual items as lowercase letters. And we're going to symbolize the predicates as capital letters. So, and the predicate's going to come first. So if we want to say Abe Lincoln was a lawyer, then we'll say capital L-A means A, that is Abe Lincoln, was a lawyer. And then we can use that sort of symbolization to combine it with our other logical operators to make complex compound sentences like this one. So if Shane is an honor student, then he is bright. So HS says Shane is an honor student. BS says Shane is bright. So it's if this, then that. Now, the lowercase letters that we're going to use to symbolize individuals, they come in 2 varieties. The letters A through W are going to stand for individual constants. That is, you can think of those as names of particular individuals, like Abe Lincoln, or that particular dog, or something like that. Now, the lowercase letters X, Y, and Z are going to be variables. And variables can stand for any individual. So they just say something like, something was a lawyer. So for example, well, we'll get into some examples in a minute, but let me get to those by introducing universal statements. Universal statements begin with the universal quantifier. And the universal quantifier is this lowercase x in parentheses. And what that says is, for all x, that is, for any given individual, something is true. All right, so the individual variables, like I said, are x, y, and z. So if I wanted to say all the s's are p's, here's how that would go. For all x, for any given individual in this domain, if that x is an s, then that x is a p. So it's different than the Abe Lincoln statement, which used an individual constant. This is using a variable. It's not saying if Abe Lincoln is s, then Abe Lincoln is p. No, it's saying if any given x is s, then it's p. So that's universally quantified. Or if we want to say all humans are moral agents, then we say for any x, for all x, if it's a H, a human, then it's an M, a moral agent. Or you can do negatives that way, universal negatives. No millionaires are tax evaders. For any given X, if it's a millionaire, then it's not a tax evader. No X that is a millionaire is a tax evader. So those are universal statements, universally quantified statements. We've got some more vocabulary to learn here. Bound variables are those variables that are governed by a quantifier. So the quantifier, remember, is this X in parenthesis. What's governed by that quantifier, what's included in its domain, is the statement that immediately follows that parenthesis. So in this case, it's everything that's in the parentheses here that follows the parenthesis X. That's all one big statement, and it immediately follows the X. So the variables that are inside this parentheses here, the X that follows the H and the X that follows the M, are governed by this universal quantifier. They're included in like the all that this is about. For any given X, if it's H, then it's not M. These X's are those that are governed by this quantifier. Now, what would happen? What do you have when you drop out, say, this universal quantifier, and you're just left with ungoverned or unbound variables? Well, then what you've got is something like this. If hx, then not mx. And we call it a statement function. It's a pattern for statements, but it doesn't have a truth value because it's not about anything in particular. We haven't said that this is something that holds true of all individuals, and we haven't said it's something that holds true of some individuals. We haven't said that this statement function applies to any defined domain. So we call the variables in this statement function free variables. And again, the whole statement function, it doesn't have a truth value, although we will be working with these statement functions a lot. And like I said, the domain of discourse is just those set of individuals over which the quantifier ranges. Those individuals that are within the scope of that statement that immediately follows the quantifier. So for example, if we have a statement like this one, for all given at, well, we've got like for all x, rx, then fx. The quantifier, for all x, doesn't govern the consequence here. The x that are f, that's a free variable right there. So this is actually like a statement function. It's not even an intelligible complete sentence. Because the quantifier only governs the Rx, not the Fx. Now, if you put parentheses around the whole compound statement, around that whole statement function, now they're all governed by the quantifier, and you've got a truth valued statement, universally quantified statement. All right, so those are universal statements. Let's look at particular statements. Particular statements are those that have an existential quantifier. An existential quantifier is a backwards E followed by a variable X, Y, or Z, and all that's in parenthesis. And what the existential quantifier says is that at least one individual, and doesn't specify which individual, at least one individual, for at least one, some, perhaps more. So if we want to say some S or P, we'd say for some X, X is S and X is P. If we want to say some S are not P, then we'd say there's some X such that X is S and X is not P. Some sweeteners are addictive. There is some X such that X is S and X is A. All right, so that's existentially quantified statements. The universal quantifier says for all X, here's what holds true of them. The existential quantifier says for at least one, for some, this holds true. Now, we've got to pay attention to meaning when we are translating natural language sentences into predicate logic. Okay, so take, for example, this sentence. All thoroughbreds are either brown or gray. And we've got the all there, so we're going to universally quantify this. For all X, if it's a thoroughbred, then either that X is brown, B, or it's G. So where the parentheses go really determine whether we got this right or not. Now, what if we wanted to say thoroughbreds and mules are quadrupeds? Well, we're going to use the universal quantifier because even though the sentence doesn't say all thoroughbreds and all mules are quadrupeds, that's what it means. It means all of them. Here's something that's true of all of them. So we're going to use the universal quantifier. Now, you might be surprised to learn that we're going to use not the conjunction sign, the dot, but instead we're going to use the wedge in order to translate this. Here's why. If we were to say for all x, x is t, if x is t and x is m, then it's q. You know what we'd be saying? We would be saying for all x, if it's a thoroughbred and it's a mule, then it's a quadruped. But that's not what we're trying to say, because thoroughbreds and mules nothing is both of those. What we're trying to say is if that animal is either a thoroughbred or it's a mule, then it's a quadruped, because nothing is both. So that's why we're going to use the wedge here. We want to say just there are plastic bags. Now you might think, well, we're talking about plural items, right? So shouldn't we use the universal quantifier? Nope. We should use the existential quantifier because we want to say there are some things such that, that is, there is at least one thing such that it is both a bag and it is plastic. Termites are insects. For all x, if it's a termite, then it is an insect. That's the same as saying all termites are insects. So that's a universally quantified statement. But I'm going to say termites are eating your house, that's going to be existentially quantified, because what we're saying is for some x, it is such that it is a termite and it is eating your house. We're not saying that all termites are eating your house. We're saying that there are some that are eating your house. Finally, here we've got some exclusive proposition. Only guests are welcome. Now, the word only indicates that what you're dealing with is a necessary condition, and necessary conditions, remember, go in the consequent of a conditional sentence. So when we say only guests are welcome, what we're saying is if you're a welcome thing, then you must be a guest. So for all x, if you are welcome, then you are a guest, even though guest comes first in the natural language sentence. Or the same idea when we say none but the brave are lonely. What we're saying is only the brave are lonely. That is, bravery is a necessary condition of loneliness. That is, if you are lonely, you must be brave. For all x's, if they're lonely, then they're brave. Even though it may not seem that way in the natural language sentence, you got to think about meaning. All right, let's look at an example here. Only sopranos are prima donnas, but all prima donnas are opera stars. Now, give that a try for a second. Pause the video and think about it. All right, you back? So only sopranos is a necessary condition of a conditional statement. That means it's going to be in the consequence. So we're going to have parenthesis. Sorry, what we're going to have is for all x, if x is a P, that is a prima donna, then x is a soprano. And then we've got this conjunction, but, and that, remember, we represent that by a dot, and then we've got another universally quantified statement. All prima donnas are opera stars. That is all. That is for all x. If x is a P, a prima donna, then it's an O, an opera star. So we had a conjunction of two distinct universally quantified statements. We'll get plenty more practice doing these. Let's take a break now.